Hello everyone, this is your junior high school math teacher, and in this video I'll discuss the 7th week lesson number 2 about right triangle similarity theorem or theorems. So after you watch the video, you should be able to illustrate the conditions for right triangle similarity theorem and prove the conditions for right triangle similarity theorem. So for our next slide, let us read this statement. In a right triangle, the altitude to the hypotenuse divides the triangle into similar triangles, wherein each of these right triangles is similar to the original right triangle. Okay? So let's just say we have triangle ABC, which is right angled at point B. And segment BT is the altitude to AC, which happens to be the hypotenuse of the right triangle. Take for take for instance this figure, triangle ABC, and this is the altitude drawn from point B to the hypotenuse segment AC. Now, as what the statement being mentioned, the altitude divides this whole right triangle into two parts, and those parts are both right triangles, and each of these parts is similar to this entire right triangle. Okay, so so uh, what I just did here is I removed those two parts from the entire original right triangle. The smaller part is this one, and the bigger part is this one. Okay, and what are the names of those parts? The smaller right triangle is named as triangle ABD, and the bigger portion of the original right triangle is named as triangle BDC. Okay, this one. Okay, and this one right here is the smaller part. Okay, now if we're going to apply one of the similarity theorems of triangles, say double asimilarity, we have the following. Okay, so as I said earlier, each of these parts, aside from being similar to one another, any of these two is similar to the original right triangle ABC. And with that, if we're going to write that mathematically, that is triangle ABD is similar to triangle BDC, which is similar to triangle ABC. And observe that we're not just uh, writing the mathematical statement for the similarity of these three right triangles. We also see to it that we establish the proper correspondence uh, of their vertices, or of the vertices between any of two of these three right triangles. Okay? Yan. Now, we know that when we talk about similarity of triangles, we are fully aware that their corresponding sides are proportional. So if we take two out of these three right triangles at a time, we can form the proportionality of the corresponding sides. Say this one, triangle ADB, this one, triangle ADB is similar to triangle BDC, this one. Okay, so we did not just write the mathematical statement of for the similarity of these two right triangles. We see to it that we establish the proper correspondence of the vertices of these two right triangles. That is, a point A from this triangle is what? Correspondent to point B of this triangle right here. Okay? And D, which happens to be the vertex wherein the right angle is located, is correspondent to point D also, where the right angle is located. Okay? And B, which is the vertex of the smaller acute triangle, smaller acute angle, is correspondent to point C, which is the vertex of the smaller acute angle. Okay? Yan. And with that, we can form the proportionality of their corresponding sides. So that would be what? Okay, but first, before we go on to the proportionality of the corresponding sides, let us consider another two right triangles out of these three. Say, triangle ADB, this one, is similar to the original right triangle ABC. So meaning, A of this triangle corresponds to A of this original right triangle. And D, which is the right angled vertex, corresponds to point B, which is also the right angled vertex. And B of this triangle corresponds to C of this original right triangle, because both of them are vertices of their respective smaller acute angle. Okay? Now, there is another pair of right triangles that we have yet to mention, and that is triangle BDC and triangle ABC, which are also similar to one another. And this one right here, triangle BDC, which is similar to triangle ABC. Yan. Again, just like the first two pairs, we uh, we also consider the proper correspondence of their vertices. And with that, let us go back to the first pair of right triangles that are similar, and we form the proportionality of their corresponding sides. So this is the proportionality, okay? Or this is the proportion. So AD over BD equals DB over DC, which is also equal to AB over BC. Okay? Then, from this proportionality, we eliminate one of the three ratios, and that is what? The third ratio. Okay? Why did we do that? Simply because the two remaining ratios have a common term, and that is segment BD. And this one right here has no presence of segment BD, so we just remove this. And from here, um, we transform this proportion solving for that common segment DB or BD. And what do we have? Okay. Of course, we do the cross product method, and then we get the square root of both sides, and the result is what? BD is equal to the square root of the product of AD and DC. Okay, what does this mean? Okay, I think we will answer that question later on. first we consider the two remaining pairs of similar right triangles. Now, I think we now go to the second pair of right triangles that are also similar. And we also establish the proportionality of their corresponding sides. And this is the proportion. And just like the first proportion, the first proportionality of the corresponding sides from the first pair of right triangles, we remove one of the three ratios that has no common segment. And that is what? Segment DB over segment BC. Because the two remaining ratios have a common segment AB. And this is now the resulting proportion. AB over AB, which is taken from this one, is equal to AB over AC, which is taken from the third ratio. So we take away the middle one. No? Then, just like what we did on this part, we solve for that common segment. So we again do the cross product method and getting the square root of both sides. So that AB, or the length of segment AB, is actually the square root of the product of the lengths of segment AD and segment AC. Okay? Then for the third pair of similar right triangles, we also form the proportionality of their corresponding sides. And this is the proportion. And just like what we did from the first two proportions of corresponding sides, we take away one of the three ratios that has no common segment. And that is the first one, BD over AB, because the two remaining ratios have a common segment of BC. Okay? And the resulting proportion with only two ratios that are present is DC over BC is equal to BC over AC. So, we transform this equation solving for segment BC. And that is BC is equal to the square root of the product of DC and AC. Now, what does these three formulas mean? What do these three formulas mean? Okay? So, now from what we have just derived, actually we have just derived three formulas. Now, ano ibig sabihin nito? Okay. So, this is the idea. In a right triangle, the altitude to the hypotenuse is the geometric mean of the segments in the hypotenuse. So it follows that segment BD here is the altitude. And this segment happens to be what? The geometric mean of the segments in the hypotenuse. And what are these segments of the hypotenuse? Actually, these are segment AD and segment DC. These are two segments separated by the altitude drawn from the right-angled vertex. Okay? So it means if we take the square root of the product of the two segments from the hypotenuse, it will give us the length of this altitude. Okay? And this altitude is known as the geometric mean. Likewise, other than the altitude, there are two more geometric means taken from the right triangle. And what are these two other geometric means? Okay, let us read the second statement. Each leg. So it means the two legs from the right triangle are also geometric mean. Okay, so let us read this. Each of the two legs in a right triangle is the geometric mean of the hypotenuse and the segment of the hypotenuse adjacent to it. Okay, so therefore, if we have AB, which happens to be the leg, it is also the geometric mean of the length of the hypotenuse and part of the hypotenuse adjacent to that leg. Okay? So, the hypotenuse is AC, and part of the hypotenuse which is next to AB is AD. Yan. Okay? So, therefore, AB is the geometric mean. Likewise, the other leg BC is also the geometric mean of what? Two segments. The hypotenuse and part of that hypotenuse adjacent to BC, which is segment DC. Okay? And with that, let us now proceed to the next slide if you don't have any question. Okay, let us have these illustrative examples. So in triangle ABC, angle A is a right angle and segment AD is the altitude to BC. Okay, this one. Now, there are some labeled segments from this right triangle, and I think we are asked to find the length of those segments denoted by X, Y, and Z. Okay, the first one, we are going to name the similar triangles involved from this diagram. And number two, we are asked to find the value of X, Y, and Z. Okay, now, for our solution in number one, okay, we have triangle ADC is similar to triangle BDA, which is also similar to triangle BAC. So this is the answer to number one. And for number two, we apply the formula for the geometric mean uh, related to right triangle, to this right triangle. So, to find the value of x, that is simply equal to the square root of the product of 4, which is the length of segment BD adjacent to this leg denoted by x, and the length of the entire hypotenuse, which is 13, why 13? But that is the sum of 4 and 9. And with that, if we're going to simplify the answer, the value of x is actually 2 square root of 13. Now, to get the length of the altitude, segment AD denoted by y, that is the square root of the product of the length of the two segments from the hypotenuse. And these are 4 and 9. Okay? So if we're going to simplify the answer, the value of y is actually 6. And for z, that is equal to the square root of the length of the hypotenuse and part of the hypotenuse adjacent to the leg denoted by small letter z, and that is 9. Simplifying the resulting value for z, that is 3 square root of 13. And this is where we end our discussion, and we'll see you again next time.